Hey everyone, thank you for being here today. This is my first time at the Autonomous Vehicle Tech Expo and also my first time in Stuttgart as well. So far it's been a really fun and enlightening experience, and I hope to come back again once, maybe next year, to present again. So if you're working anywhere near ADAS or autonomous vehicle development, you know that data collection is no longer the big issue here for us. The big problem that we have right now is that we're swimming in data. So there is so much data being collected. Now we have to think of other topics to cover instead of just data collection. So we log petabytes of driving data. And as engineers, we have to ask ourselves the question of what subset of this data do we actually need? So what part of this data is actually informative and what we actually want to look at instead of just collecting more and more data, which is redundant. So by the end of this presentation, I hope to shift your focus from just collecting data to actually distilling it down to what actually matters and to scenarios that actually drive safety and performance. Before we dive deeper, I'd like to give a quick introduction into myself and my company. So I am Mihailo Milic. I'm a senior machine learning engineer and I work at Autometric, on behalf of which I'm giving this presentation today. I'm also a PhD candidate at the University of Novi Sad in Serbia, where I work on distributed machine learning, namely federated learning, and hopefully by the end of the year, I'll be able to remove the candidate part from my title, so wish me luck with this. So at Autometric, what we're doing is we're building an end-to-end solution that takes in massive amounts of unstructured data. We then help users distill this data down into some form of actionable intelligence. Finally, our platform helps clients curate their massive amounts of data, so select the parts that actually matter, offers compute and service engines to drive this intelligent decision-making that goes later on in the process. In short, the goal of Autometric is to ensure safe ADAS systems. And how do we ensure this? Well, through informed ADAS validation, the emphasis being on the informed part. Our product ultimately shortens time to market, and it reduces the total program cost. At the end of the day, clients actually need to provide evidence of compliance to be able to fulfill their SOTIF and other critical ISO standards required for certification. So what does this roadmap usually look like? It starts off with identifying hazards and then doing some sort of risk assessment. Now, the outcome of this risk assessment could go in two ways. So you can either conclude that there's not much risk in this regard. In this case, you're okay, and you can just keep doing what you're doing. On the other hand, you can identify that there exists a big enough risk involved in this hazard that you actually need to think of some mitigation strategies, right? So if this happens, you go to the next step where you define safety goals, after which you define safety requirements. And then once this process is done, there are multiple paths you can go down. So one such path is applying safety functions to your processes to mitigate these issues, right? A simple example is just identifying certain scenarios in which some of your components do not actually work as expected, and you can just then turn these components off and notify the user about this. So this is just a simple way of applying some sort of safety function. But I'm not going to be talking about this today. If you're interested in this, you can go to our booth, to our partners, the NIT Institute, which are co-located at the Autometric booth, and they can tell you more about this path. Today I'll be focusing more on a different one, and this is respecification measures. So you could go down this path to validate safety KPIs to ensure that you have good coverage and you are robust on out-of-distribution data points or data samples, which are also called edge cases. And this is where Autometric comes in. To understand the importance of our infrastructure, we have to look at the reality of testing today. So the problem essentially boils down to the struggle between volume and value of your data. We can look at the chart that we have on the slide to my left, and we can take a look first at the blue curve. This blue curve represents validation scale. So as this scale keeps increasing, it means that we are collecting more and more data in our data sets, and this means that we need to validate more and more data. So think of capturing kilometers upon kilometers of highway driving during sunny weather and perfect weather conditions, right? The green curve, on the other hand, it first starts off following the validation scale, after which it plateaus and then starts to dip. Why does this happen? Because at some point, it gets increasingly more difficult to sift through all of the data that you have and to find those edge cases that really matter. So normal data points actually drown out those edge cases which are more important for you to be able to validate your safety KPIs. And this is the entire point. So more normal points makes it harder to find the edge cases that are problematic and that you need to focus on. By the end of the presentation, you'll be shifting your focus from the volume of data to the value of data. Handling enormous data sets comes with numerous challenges. Just to name a few, you have high storage costs, increased compute time, manual data curation time. You also have some development time involved in this, and just the pure logistics of handling massive amounts of data. The big takeaway here is that not everything should be reviewed equally, and that the scale of what we're trying to validate actually grows a lot faster than what engineering teams can effectively review. That's the biggest problem. The engineering capacity to review data is finite, and this is a problem when you have numerous data sets and massive amounts of data that you're collecting, which actually hide the needle in the haystack for you, right? So the problem is finding that needle in the haystack. And in some cases, I'd go as far as to say that you also have to focus on finding hay in the haystack, because some of these edge cases are so much similar to the normal ones, but differ just slightly, that it's even harder for you to find those edge cases than you would expect. Now I'd like to take you back a couple of hundred years to the 16th century to show you that data distillation is not a new thing. It was important even back then. So the astronomer Tycho Brahe, he spent decades accumulating the most massive and meticulously detailed data set on observations of celestial bodies in our solar system. And he collected pages upon pages of these logs manually and literally by looking out into the sky with his own eye. His assistant was a guy named Johannes Kepler, and he really wanted to get hold of this data to analyze it. So there was some push and shove between the two, but ultimately Kepler got his wish and he got access to this data. And what did he do with this data? Well, he took it and turned it into three elegant formulas, now known as the Kepler's laws of planetary motion, right? So what did Kepler do? He took these mountains of papers, distilled them down to three formulas, and then he didn't need those logs anymore. So the mountains of papers became obsolete, essentially. At Autometric, what we're trying to do is we're trying to help clients move away from that pure data collection phase that Tycho Brahe was in, and help them push forward to actually becoming the Keplers of their time, right? So smart data distillation is what's going to help them achieve this, to transform their data into actionable intelligence. Our primary focus is uncovering scenarios in real-world data. Instead of just simulating and generating your scenarios, we focus on finding what's hidden in the data sets you already have collected. What we offer as a platform is not just limited to real-world data, but our philosophy is that real-world data is richer. Simulation is important, but it is limited by the imagination of the engineers that are creating those scenarios. Our main argument for focusing more on real-world data is that real-life scenarios are weirder than anything you can think of on your own as an engineer running simulations. The real data captures the messy physics, the weird edge cases with weather, and unpredictable human behavior that can surprise you at any time while you're on the road. Instead of just spending your time generating synthetic data sets, we help you find the information that you already have, but it's hidden in the data set you collected yesterday. That is our main focus. So, To move to a concrete example, this is a data set that you might have heard of. So this is the NVIDIA Autonomous Vehicle Dataset. And if you look at the raw specs, you can see that it has 1,700 hours of driving, which totals out to 133 terabytes of total file size. Well, my question to you is, do you actually think that this data set only had 1,700 hours of driving? Probably not. I'm going to tell you that it definitely did not, because it started out as a massive and unmanaged stream of raw data. So this data had to be curated before it was released, and then it totaled to 1,700 hours. Even after this preparation, this is still a lot of data, and interesting scenarios are still only just one small part of this data set. So production data sets can be even more massive, because they can be collected for months or even years, and the results can be hundreds of petabytes big or large, right? So for reference, if you have 50 petabytes of data, that is equivalent to 170 years of HD video. So this is a lot, right? Now we have to see what does it actually mean to choose what's important in your data. So a typical ADAS data set looks like the chart here on the slide, which has a long tail distribution shape. What does this mean? So we have two parts of this data set. One is to the left, and it's colored blue, and the other is to the right, and it's colored green. So the left part is called the head of the distribution, and these are the normal or high volume cases, so stuff that happens a lot. So driving down the highway, it's sunny, there's a couple of cars, nothing special is going on. This data is easy to collect, but it has diminishing returns. So the more you collect it, you're not learning anything new from it. The real risk lies to the right, and this is where engineering focus must be shifted towards too. So it has infinite variety of edge cases. So the things that surprise you may get drowned out by the massive amounts of normal data. If you try to solve this issue by collecting more data on your own without any plan, this can just backfire on you, because the problem will get worse. The edge cases will get even more hidden by the normal data points. So every extra terabyte that you collect makes the problems worse by diluting these edge cases. When we talk about solving this issue at Autometric, we lean on the idea of data distillation. So data distillation means that you want to reduce the amount of data that you work with, but in a smart way, to focus only on what really matters. A good analogy of this is if you're, comes from sports, right? So if you're watching a football game that lasts 90 minutes, that's a fairly long time when you compare that to a set of highlights that get generated after the game ends, right? So the highlights, they are rich with data or information that is only on the important parts of the game, while the entire game in itself only has peaks at certain points, right? So distilling data is essentially turning that 90-minute game into a set of highlights. Data distillation can be done in multiple ways, but today I'll be quickly explaining two possible ways of doing this, right? So first, we have what we call general distillation, and this focuses on the statistics of your data set that you have collected, right? The goal is to reduce the size of the data set while keeping the statistical distribution the same. So you pick and choose the points so that the smaller set, the subset that you select, ends up looking like the bigger set that you started from. This is a good approach if you're looking only to optimize your storage capacities and your efficiency on computing what you need on that data. The second way that we're going to be discussing today, and which is more important for us, is uncovering edge cases. So this is more important for validation, where we purposely steer our attention from the head of the distribution to the tail end of the distribution. These edge cases are defined through the domain of the problem that you're trying to solve, or the client is trying to solve in this case. So if we're talking about, I don't know, sign detection, edge cases could be detecting signs in severe weather conditions like heavy rain, let's say, or occluded signs due to the windshield wiper being in the way, or something similar to this. These could be edge cases. We named the Smart Data Distillation approach Scenario Prioritization Ranking, or SPR for short. This technique, SPR, has been used extensively on clients' data, but this cannot be shown here, so we conducted a study. using a publicly available autonomous driving dataset, the Waymo Open Dataset. Here, the use case that we tried to apply this problem to was detecting cyclists in the dataset, using only the front camera feed. So, in total, 33 training runs were conducted on various types of detectors, and then an average precision score was extracted for all of these training runs with 4 different dataset strategies. So the first strategy is just using the entire dataset of 150,000 frames. The second approach was the first distillation approach, which we do not use, but this is essentially sampling at regular time intervals. So taking every 100th frame into account, right? By this, we reduced the size to only 1% of the original data set. After this, there was a second approach to data distillation, which is just random sampling. So this was used as a baseline. And finally, we applied our SPR baseline approach, the generalized SPR that I mentioned, to reduce the data set size to only 1% of the original data. What ended up happening is the following. So we had an average precision of 56% on the first baseline data set, which is the entire data set. Random sampling underperformed, which was as expected. Sampling frames at specific intervals also did not function quite as well as training on the full data set. But in this set of experiments, SPR actually outperformed the baseline scenario where we used the entire data set. This is probably explainable by the fact that by reducing redundancy in the data, actually helped it not to overfit on some of the cases that we had. This was a longer study, and we published a white paper on it, and you can request that white paper on the link on the QR code that we have right now. It's going to take you to our site, where you can request access to the white paper to learn more about how we did this. So now that you've reduced the size of your data sets using SPR, and you focus specifically on that tail end part of the distribution, you're now ready to validate your KPIs in your important scenarios that you defined, right? So our solution supports this entire process from the data collection phase all the way to the result visualization. So initially, when you start collecting data, there usually exists a planning phase. So our software also supports you to plan out your data collection needs. You may, for instance, want to collect driving data with 70% of it being in cities and 30% of it being on highways. So you can plan out this, then run data collection. And while you're running data collection, you can upload data to our platform, where then you can create your own custom KPI validation rules through our KPI authoring tool, a screenshot of which you can see now on the slide. There's a simple graphical interface, and it makes it easy for anyone to actually jump in, define rules with simple questions, and form this kind of tree to actually label their KPI events that happened during the course of those drives. By combining this feature, the KPI authoring tool with our SPR feature, you can do strategically targeted validation on specific subsets of the data that represent the most critical scenarios in your dataset. Once validation is done, you can open up various reports, including detailed reports on each individual drive, like you can see on the slide right now. And you can click through your data set and see where your components fail to produce satisfactory results. Through this approach, you have pinpoint accuracy in determining where additional effort is needed, if any. As a final message, I'd like to leave you with this, that the challenge no longer lies in collecting scenarios. It is now continuously identifying the ones that matter the most. That's everything for me today, so thank you for your attention. If you have any questions, we can cover them now, but I strongly urge you to visit us at our booth, which is A168, which is just around the corner from this live stage, so you can swing by and we can show you live demos for everything that I've discussed, and even more, because there's a lot to talk about in 20 minutes. So thank you very much. If you have any questions, I'm open to those.